Okay, in this question, there's a beaker which contains 0.005. 0.005 is actually half kilogram. So that is the mass of the water, and it is at a temperature of 3 degrees centigrade. That's a starting temperature. The beaker is heated and the internal energy increase, like how much energy we supplied or energy increases by 21 kilojoule. So if it is 21 kilojoule, you must convert into joule. So 21 kilojoule means, because to convert kilojoule into joule, you have to multiply by 1000. So it means it will be 21,000 joules. The specific heat capacity of a water is 4200. That is the value of the C is given. This was E. In the question, what is the temperature of a water after it has been heated? So we have a container which is filled with water. The starting temperature of the water is 3. We supply 21,000 joules and the specific heat capacity of a water is 4200. The question is, what is the temperature after it has been heated? We need the final temperature. So how we can work out the final temperature? First, we should use the formula for specific heat capacity. The specific heat capacity is equals to energy divided by mass into temperature change. In some books, they write temperature change as delta theta. That is right. You can use that. Or if you want to use temperature change delta T, that is also correct. So first what we will do, we will find the final temperature, and after getting we will find the change in temperature. Delta T means change in the temperature. So first we'll try to find the change in temperature, and from change in temperature we can work out the final temperature. So specific heat capacity of the water is 4200. Remember, if specific heat capacity is joule per kilogram, the mass should be in kilogram. If sometime in some questions it is joule per gram, in that case the mass should be in gram. So don't forget to convert the unit depending on the units of specific heat capacity. So here specific heat is capacity is joule per kilogram degree centigrade. So we need a mass in kilogram, which is already there in kilogram. So specific heat capacity is how much? That is 4200. Energy, that was 21 kilojoule, but it should be in joules. So we multiply by 1000. So this is 21,000 joules. Divided by mass, how much mass is there? 0.5 into temperature change, delta T. So if I need delta T, because this delta T is divided, other side it will be numerator. And this 4200 is in numerator, it will come there in denominator. So when I just switch the position for delta T in 4200, so 0.5, and this will be 4200. So when we simplify this, the change in the temperature, the delta T will come out as 10 degree. But in the question, we don't want change at that temperature. We want the final temperature of the water. The temperature of the water after it has been heated. Delta T is the change in temperature. So example, if you have a container that was filled with water, if the initial temperature was 3 and we calculated that the temperature of the water has changed by 10. So if the temperature of the water is changed by 10, what is the final temperature, or what will be the final temperature? So that will be 13. And you can use a formula as well. How you can use a formula after you get delta T, the change in temperature? Remember, the temperature change is always the higher value. It's not like final minus initial. It is always the higher value minus the lower. Whenever you are supplying heat energy, the final temperature is higher. So in this case, the temperature change will be T2 minus T1. So temperature change is 10, which we calculated. The final temperature we don't know, and the initial temperature was given 3. So this was 3. If this is minus 3, if something is subtracted on one side and will move to other side, it will be added. So it will come out as 10 plus 3. So 10 plus 3 is what? 10 plus 3 is 13. So C will be the right answer. Is it clear, this question?
Yes, sir, clear.
In question 15, the substance loses the thermal energy to the surrounding at a steady rate. Remember, whenever the temperature is not changing, it means that moment state is changing. So in this region, there is a change in state. In this region, there is also a change in state. So if we try to label the position, so first it's a cooling curve. So first we have a gas. Then at this point, the gas is turning into liquid, like it's condensing. And then we'll have liquid, and then from after Q the liquid is turning into gas or liquid is freezing. The question is, what could the portion P and Q represent? A gas condensing is not from P to Q. A gas cooling is this region. This is a position where gas is cooling. Liquid cooling, that is true because in this state from P to Q there is a liquid and the temperature of the liquid is decreasing, or we can say the liquid cools down. And liquid solidify after Q, not between P and Q. We want to tell between P and Q, so that's why C is the right answer. Okay, another question. A student, this is a thermometer. A student wishes to check the upper and the lower fixed point. Upper fixed point, look, remember, upper and lower fixed point are not reference to what thermometer is reading. It is always a fixed number. That upper fixed point means 100 degree and lower fixed point means 0 degree. So it does not have anything to do whether thermometer is having that number, but we call upper and lower fixed point because we know these points are always fixed. And how we can mark the upper and the lower fixed point? If we place in a pure melting ice, we can mark the lower fixed point, and if we place in a pure boiling water, we can mark the upper fixed point. So beaker P contain a mixture of ice and salt, so it is impure. If it's impure, we cannot, because impure substance will have lower melting point, so it does not melt at zero, or impure ice here. Beaker Q contain a mixture of ice and water. Ice and water, basically ice and mixture of ice and water means melting ice. So that is true. Like we can use it to mark zero. A beaker R contain a boiling salt solution. Again, impure water. Salt solutions are impure water. Like salt contain other particles. So it will boil at more than 100. It won't boil at 100. And containing a boiling water. So if it's a boiling water, it means pure boiling water here. As they did not mention anything about the impurity. So we consider it as a pure. So Q and S can be used to mark the upper and the lower fixed point. So for thermometer, the upper fixed point is the temperature of a pure boiling water, whereas lower fixed point is the temperature of pure melting ice. And it is always fixed, it never changes. Like whenever you want to mark upper and lower fixed point, you mark in this manner. Two identical cars are there. One is a black car. So one is a dark color car. Another one is a white car, a light color car. And they are at the same starting temperature. Like example, if I say the temperature of the black car is 20, the temperature of the white car is also 20. The car are left in a bright sunshine and their temperature increases during a daytime. So as we know, dull and dark surfaces are good absorber. So what will happen during a daytime? This will absorb more energy and the shiny surface will reflect most of the energy. It will absorb some, but mostly it will reflect. This will absorb most and small proportion will be reflected. So if it is absorbing more energy, what will happen? What will the temperature rise? Dull and dark surface will absorb greater amount of energy. So if it was 20, then maybe it will become 25, and this was 20, it might become 22. So during a daytime, which one shows a greater increase in the temperature, the dull and the dark surface, black? Then which car shows a greater rate of temperature increase and which car shows greater rate of temperature decrease? Like which one? Because as we mentioned, dull and dark surfaces are good absorber and good emitter. So during a daytime, when they absorb energy, the temperature rise is more. So during a daytime, the dull and dark surface there's a greater change in temperature or rise in temperature. But at night, what happens? Now they have to remove the energy, they have to release the energy because there is no source of energy from the surrounding. So at night, what will happen? As the dull dark surface, because during a daytime it absorbs lot of energy, so at night it will start to release that energy. So most of the energy will be released because it absorbed greater, so it will release more. So when it will release more, the temperature will fall to a lower value, like the greater change in temperature will be there. So dull and dark surfaces, increase in temperature is more and decrease in temperature is also more. Like example, now it is 25, when it cooled down it returned back to 20. So when 25 turned to 20, it means the temperature changes by 5. Whereas a white car, because it does not absorb too much energy, so it does not radiate too much, and its temperature fall will be smaller. So both cases, the black car will absorb greater energy and increase the temperature, and when it cool down, it release more energy and there will be a greater change in temperature. So dull and dark surfaces are good absorber. During a daytime, it is absorbing most of it. And at night, it start to release that energy. So greater amount of energy stored or greater amount of energy is trapped by the dark particles, or you can say dark material. And surrounding cool down when the surrounding cool down, they start to emit out that energy which they absorb during a daytime, so it will cool down faster. Now it's winter, you can also do this a simple experiment. If you at night you try to touch any of the car, like example a dark black or a matte black color and a shiny white car, you will find, so you will find when you touch a dark color or a matte black car, it will have a low temperature as compared to a shiny car. So dull and dark surfaces are good absorber, good emitter, whereas shiny, they are, because it release, whenever object is at high temperature, it release more energy as compared to object at low temperature. So rate of energy emission for dull and dark will be higher as compared to shiny. In this question, the liquid is heated in the beaker. Whenever you are heating a liquid or a gas, that the process by which heat energy transfer, we call that as a convection. So what happens when you supply the heat energy, the particles near the heat source, they gain energy, they move away from each other. As a result, when they move away from each other, the density of that region will decrease. When the density decreases, that region, the particle will rise, and the other particles which are closer will come down. So the density of a liquid changes as the temperature increases. This may cause the energy to transfer. Liquid and gases, what is the method? Conduction is for solid or between the two different surfaces. So it can be B or C. Then what happened to the density when we supply? Because when we supply energy, the substance expand. If the substance expand, the volume increases. If the volume increase, the density will decrease. So decrease in density, and there is a convection. Whereas the last question, no, 20 is more are there. Okay. Sound waves having a frequency of 2 kilohertz. This is the frequency is given 2 kilohertz. So 2 kilohertz you have to convert into hertz. So 2 kilohertz means 2000 hertz. And it passes through with a speed of 800. That's the speed. What is the wavelength? So formula which relate the frequency, speed and wavelength. The formula is V is equals to F lambda. So speed is equals to frequency multiplied by wavelength. So when we multiply, we'll get the the speed is frequency times the wavelength. So speed is equals to 800, frequency is 2000, and the wavelength we don't know. So 2000 is multiplied, other side it will be divided. So 800 divided by 2000. So it will be 8 divided by 20. So when 8 is divided by 20, the only answer which is less than 1 is A. So that's why 20A will be the right answer. So remember, whenever any kind of wave is there, the formula which relates speed, frequency and wavelength, V is equals to F lambda. Which row shows the nature of a light? As we discussed, sound waves are only longitudinal sound waves, and wave in a compressed spring, they are longitudinal. Rest all of them are transverse. So light waves transverse in nature, sound waves longitudinal, and X-rays also transverse. So C will be the right answer. So you have to learn these examples. Just remember the longitudinal example and rest all will be transverse. Then the diagram shows a light is traveling from air to glass. So whenever light travels from air to glass, the formula for refractive index is sine angle I over sine angle R. Which formula is used to calculate the refractive index? So angle of incidence is from normal to the incident. That's called angle of incidence. So that will be sine W divided by the angle between the normal and the refracted. That is angle R, the angle of refraction. So that will be sine X. So sine W divided by sine X when we divide, so it matches with option D.